Good morning, everyone. I'm going to be going through some of our new features for MIRI for Cycle 6. We have quite a few new things coming. So my colleagues from the other instruments went into quite a lot of detail for their new, all their new capabilities and features. Um, for me, I won't have time to go into a huge amount of detail because we have quite a few different things that are new that I want to highlight. So here's a quick summary. We have our wide field slitless spectroscopy modes in parallels. We have new subarrays. We have a new readout pattern that is going to improve performance. And I'm going to talk a bit about some target acquisition changes we are making. We do have a couple of recent SPIE papers that are on the archive that go into more of what I'm talking about today. So there's one I led, which is very similar to what I'm talking about today. We have another one from Andrea Petrick, specifically about the status of the wide field slitless spectroscopy mode. And then also to reference the previous JWebbinar, which focused on APT and ETC, but because MIRI has a lot of new things in there in these tools, I think some of our changes were also covered in that JWebbinar. So you might find those materials interesting as well. All right. I'll begin with talking a bit about our wide field slitless spectroscopy mode. This is still quite a new mode. So it was offered for the first time in cycle 5. So it's not new for cycle 6, but it was new in cycle 5. So we're still in very early days of this new mode. So prior to cycle 5, we had 2 low resolution spectroscopy modes, essentially. So where the dispersion is done with a prism that's mounted in the imager filter wheel. So this is actually kind of part of an imager module of MIRI. Both of these modes are called the low resolution spectrometer, but in one mode of operation, we use a fixed slit. I've indicated a little diagram of the imager focal plane indicating the location of the slit. And we also have a slitless mode, which is specifically targets time series observations, so transiting exoplanet systems, other types of time variable targets. The prism dispersion covers 5 to 14 microns in a single exposure. A resolving power of around 100 in the middle of the range. It varies from about 40 at the 5 micron end, goes up to about 160, 160 to 200 at the red end. The fixed slit LRS mode is always read out in full array. And then for slitless, we use the slitless prism subarray. It has the same wavelength coverage, same resolving power, but dedicated to time series observations, and in this small subarray, which reads out much faster than the full array to enable brighter targets. So we're leveraging the capability of the double prism with the larger field of view of the imager mode to develop this wide field slitless spectroscopy mode. So it has the same wavelength coverage, same resolving power, only that any targets in the imager field are all dispersed. So this already actually happens because the LRS slit mode, we read out in full array, so any targets that happen to be in the imager field are already dispersed. So that's an example that you see in this figure here. There's actually a lot of wide field slitless spectroscopy data in the archive. So that's the background for the wide field slitless spectroscopy mode. It will be used for the first time in cycle 5 for science. We are still working on pipeline and calibration reference files. So we have been taking a lot of calibration data in the past year. And working on fully integrating MIRI into the wide field slitless calibration pipeline. Of course, NIRISS and NIRCam have these modes as well, so there is already some infrastructure in the pipeline for those modes. And so, so for more details about the status, the calibration data, do check out Andrea Petrick's paper, which is on the archive, which I linked on that front slide. Then you can actually see examples of the calibration data, how we're working with it. And as the other presenters have said, calibration data is publicly available as soon as it's taken, so you can access those in the archive as well. So then the new thing is that for cycle 6, we are also enabling the wide field slitless spectroscopy mode in parallel. For cycle 5, it was only available as prime. We now have it available as a coordinated parallel with NIRCam imaging. So the MIRI wide field slitless prime plus NIRCam imaging in parallel. I'm showing here on the slide just a diagram of the focal plane for the whole observatory. So you can kind of see, as a reminder, coordinated parallels, if you observe with two instruments at the same time, you're not looking at the same field. They are separated. We also offer the wide field spectroscopy mode as pure parallel. So this is where we don't have like a dedicated APT template that optimizes for both of the modes, but the pure parallel mode kind of piggybacks on other observations. Please read the documentation, read the call for proposals. There are some dedicated tools available, I believe, to help prepare pure parallel programs. But this is going to really make this mode give a lot more options for using this mode. Wide field slitless spectroscopy on the near infrared instruments have been very successful in use with in parallel with other instruments. So I think this is going to create a lot of new possibilities. Okay, that's for wide field slitless spectroscopy. Next up is new subarrays. This has been a really big project we've had going on in the last year, 18 months or so. Here you can see again a diagram of the imager focal plane. So in the previous view, I had highlighted where the LRS slit goes, where the spectrum is dispersed, and this slitless prism subarray. I already mentioned that. We have several more subarrays for imaging. So bright skies, sub 256, sub 128, and sub 64 up there in the top. And then we have a set of dedicated coronagraphic subarrays. So each of these mask subarrays is tailored to a particular mode for our coronagraphic imaging. These subarrays, as others have already mentioned as well, they allow for faster readout times, increasing the dynamic range, so giving access to brighter targets, and also they reduce the data volume as well for very long observations. Subarrays, particularly the very small ones, they very regularly get used for observations as well. We can look at very bright targets for a very long period of time. Now, from quite early on in the mission, we had noticed some problems with our subarrays in that a number of them were affected by electromagnetic interference noise patterns. So this is some of these noise patterns are subtle. Sometimes it is a lot more marked. It kind of depends a bit on which subarray and also on the kind of exposure configuration. You can see here in the figure on the left, that's those of you who've done time series observations with the MIRI LRS are probably familiar with this view. So you get this kind of banding that also kind of travels through, if you have many integrations, as you scan through the integrations, you see this pattern sort of traveling up and down the subarray. We have a really detailed technical report, which I've linked here by Brandt, Bergeron, and Clark, all at SCSTI, who, first of all, demonstrate in a lot of detail like how this pattern arises. They kind of really go through like the basic physics of it, how this works, and why it looks the way it does. And also they describe the algorithm that we've had in the pipeline for a couple of years now to eliminate it in the detector 1 pipeline stage. The most prominent frequency for noise is 390 hertz. That's probably, if you have dealt with this, that's probably what how you've heard this referred to, the 390 hertz noise pattern. There are actually some other frequencies that affect different subarrays. There's also a 10 hertz noise pattern, which actually affects the full array and all the subarrays, but which is at a much lower level. This 390 hertz noise is the most prominent. It can be challenging to remove. It can be, particularly for very long time series, it can be very time consuming to run the step to remove it. And we've basically known all along that by if we just slightly resized the subarrays or created new ones, we can actually just eliminate this. We can avoid it from happening in the first place, which is of course very attractive. It means there's less pressure on this pipeline step. So we kind of decided to go ahead with that strategy to define a new set of subarrays specifically addressing the 390 hertz noise, which we know has been a challenge for a lot of the time series folks. And these now, the new subarrays will have sizes and locations whose readout, whose sort of clocking pattern is in phase with that 390 hertz frequency. So it's really a matter of ensuring that the number of pixels in the array and where exactly it is on the detector, the way that it's read out, is in phase with that frequency. So that's something we have been working on for a while to implement and are basically ready to offer this for cycle 6. So again, this is also described in more detail in the SPIE paper that the Kendra et al. SPIE paper that I linked at the start. We see here once again, the image focal plane, showing the ones that, basically the new subarrays against their sort of legacy values. So Bright Sky and sub 256 and the coronographic subarrays are not affected by these changes. Sub 128 and sub 64 have got a new counterpart. So these have an underscore IP, sub 128 IP, sub 64 IP. They match the old ones very closely in location and readout time. So we've really just slightly tweaked them to make them in phase with that 390 hertz frequency, just so that it keeps it very easy to switch from one to the other with very little impact on the time, or the brightness limit is essentially the same. So it's less than 5% difference in readout time. And I'm just showing here, I've shown the table here, which is on JDocs, which is in the paper, is documented everywhere, showing the size to the new subarrays. I've got a little asterisk next to them, shows the size compared to the old one, and the read time as well. And so you can see they are extremely close. These whole new set of subarrays is included in APT since May, I believe, APT 2026.3.2. and in the cycle 6 version of the ETC. So you can already go in there in the ETC and do your calculations for these new subarrays. I haven't mentioned the LRS ones yet. So we have some. So we've applied these changes also to the slitless prism subarray, which was one of the modes where people would. We heard that it would cause problems. So we've actually, because we were defining these new subarrays, we decided to make a few additional enhancements for the LRS mode specifically. There was an additional problem with the slitless prism subarray in that it sort of straddled part of our focal plane mask. So we had this region here in the middle of the subarray, which these pixels often showed quite different behavior. And so in this figure here, this is from a paper from a few years ago, shows this. It affects a number of our time, sort of a significant fraction of time series we take. So where you get this discontinuity that coincides exactly with this region on the detector. And that proved very, very challenging to kind of calibrate out. So we know that basically this region of the detector, just at a pretty scientifically valuable wavelength range, people were having to really just eliminate that from their data, which is really, not what we want. So when we were redefining the new subarray, So the new slitless prism IP subarray, we actually moved it up as well, so that this problematic region is now in a part of the spectrum where our signal to noise is quite poor anyway, so more towards the red end of the spectrum. And in addition, we've created a new slitless prism IP short subarray, so IPS, which actually cuts off the shadow region completely, reads out faster, so it gives a little bit of extra dynamic range, but it only goes to about 12.5 microns. So we do lose a little bit of wavelength coverage, but this is in an area where our throughput is quite poor anyway. And so it gives you that extra brightness because of the shorter read time. And then finally, we also, for the first time, defined a subarray around the slits. So for the fixed slit LRS observations, I said at the start, we always read out the full array. Well, now from cycle 6, that's not true anymore. So we have defined a sub-slit subarray that has 9 times higher dynamic range. So that now also with the slits, we can go to brighter sources. So I think particularly for LRS here, both the time series and regular LRS slit observations, with these new subarrays, we are creating quite a lot of new opportunities and improvements in the data quality for cycle 6 science and beyond. I wanted to include one slide on the kind of transition for this. Again, another nice view of the focal plane, highlighting these new subarrays. So they are available in APT and ETC alongside the legacy older subarrays for cycle 6. So we are keeping the legacy set of subarrays also available in cycle 6. And the new ones will give better data quality, but there may be reasons why people want to maintain consistency with previous observations. You might want to observe a target that was previously observed with one of the subarrays, and you want the observations to be the same. There are, I think, some good reasons why you might want to still use the old subarrays. So we do keep them available. We likely will deprecate them in future cycles. But for now, the old and new are all available. The new subarray definitions only address 390 hertz noise. So there are some other frequencies like the 10 hertz, for example. These are generally far less impactful, but having the new subarrays doesn't mean we can just switch off the EMI core step. So we still have the EMI core step in place, but we will not need to use it for 390 hertz noise. So there are probably a lot of observations that wouldn't be affected by EMI noise at all. These other frequencies tend to be much, much weaker. We're also not updating the chronographic subarrays. They are affected by 390 hertz noise, but generally we have found that with all the data processing and reduction steps required for chronography, we have found the impact isn't as severe on that science. And also because the calibration effort for chronographic imaging is a lot more work than for these other modes. So the sort of trade-off of resources required and benefit was a little different, and so we decided to leave those as they are. Some cycle 3, 4, 5 programs that have not yet been executed may also be able to transition as we get calibration data and have confidence that everything is working well and are able to produce new calibration reference files. But we will be looking at that on a case-by-case basis. If you're in that situation, please do contact us via the help desk, and we will look into that for you. But for cycle 6, they will be available. Okay, so that's on the subarrays. Next up is a new readout pattern that we're offering for science observation. So this is relevant for any of you who use the slow R1 readout pattern. So our default readout pattern is called fast R1. So it's basically each pixel is read once per group read, and that gives, for the full array, that gives a read time of 2.775 seconds. We created a second readout pattern called slow R1, where each pixel is sampled 8 times. And so this gives a full frame read time of 23.89 seconds. And so we recommended that for very long observations in low background regimes. So with the idea that sampling a pixel 8 times would beat down the read noise significantly by square root of 8 approximately, and also to reduce data volume. We also have a set of readout patterns called fast group average N, where N could be 4, 8, 16, 32, or 64. These were developed specifically for target acquisition. So target acquisition is performed fully on board, and the amount of data that can be stored on board during the target acquisition for the target acquisition like algorithm is very limited. So this was a way of allowing TA on fainter sources without increasing the data volume. The fast group average modes, they don't read the pixels n times. They do fast reads like the fast R1 mode, and then the frames are averaged kind of outside of the detectors. So it's sort of the effect is a little similar to slow R1, but the way it is technically implemented is different. We have a lot of literature on exactly how our detectors work. I've listed there a few papers, and we also have a page on JDocs with lots of technical reports and papers about the instrument. Now, the slow R1 readout pattern we've known for a while isn't actually as attractive as we had hoped it would be. It turns out it doesn't beat down the readout noise by square root of 8. It's actually the readout noise is it only brings down the read noise very slightly compared to fast R1. I'm showing here like histograms of the read noise. So in that sense, the benefit wasn't great. And then also, and perhaps more importantly, when we switch between fast R1 and slow R1, it's a kind of a state change in the detector, and it causes thermal settling artifacts, particularly marked in the MRS. So unfortunately, if you were to use the MRS in fast R1 mode, after a program that used slow R1, you could get this sort of fading glow in your detectors. And so these 4 images here of one of the MRS detectors is a sort of time series of that glow fading. So obviously that's something that we really didn't want. And so we've only really been recommending slow R1 for data volume reasons. So only if you really need to reduce data volume. And so we've now decided to start kind of phasing out slow R1 and replacing it with fast group average 8. So slow R1 reads the pixel 8 times. The fast group average 8 just takes 8 frames and averages them. So in terms of the frame read time, they are very similar. But because the fast group average modes aren't a detector state change, the averaging is done outside of the detector. It's much more attractive in terms of not causing those artifacts in the data. We also see, sorry, on the previous slide, it does successfully beat down the readout noise much closer to that square root of 8 factor. So it gives lower read noise and no artifacts. As with the subarrays, we're going to keep both slow R1 and fast group average available for cycle 6. There may be people who want to use slow R1 for consistency with prior observations, but fast group average 8 should be the default readout pattern if you need to limit your data volume, if you're doing deep, low background observations where you might be read noise dominated. That's particularly in the MRS and shortwave imaging observations, that can be the case. The fast group average modes, all of them remain available for target acquisition as well. So there are no changes there. So it's really just that we're taking one of these fast group average modes and making them available for science exposures as well. And I think this is going to be a really nice improvement. Okay, so finally, I want to talk a little bit about target acquisition. This is it's slightly different in that this is actually not something that as the user you need to choose. But this is something that we're changing slightly in our operations of target acquisition to basically make target acquisition a bit more robust. The LRS mode, the chronographic imaging mode, heavily used target acquisition for these modes is extremely important. For the MRS, most observations don't really need to use target acquisition, but there are some observations of point sources where that can benefit from acquiring the source with TA to improve removal of systematics like fringing patterns. We have a list of requirements that we have documented in JDoc. So things like the coordinates and proper motions are very important. They have to be point sources with a known brightness. They've got to be the brightest source in these TA regions of interest, which are typically about 5 by 5 arc seconds. High signal to noise, no saturation. But we have had target acquisition failures, and these can be quite impactful. We have a technical report that's just being finalized right now, where one of our team looked in detail at all the LRS slit target acquisition sequences, so more than 400 of them, found generally a very good success rate, but we really wanted to dig into why TA was failing. Because it's a small number, it's a relatively small percentage, but they can still cause, idle time. They can still disrupt the schedule. They might require repeat observations. So they are, kind of impactful, and we want to avoid that happening. We actually found the majority of failures were due to user errors. So this is actually also wanted to take this opportunity to really remind people of the requirements for successful target acquisition. But there are some cases that are unpredictable in our current way of operating, are unavoidable. So hot pixels that are unmasked, we know the number of hot pixels increases with time. We try to monitor that and make sure that we update the masking on board on a regular basis. But there have been cases where a hot pixel has popped up in a region of interest and has been brighter than the source. It's very difficult to avoid. Similarly, a cosmic ray stripe. Some cosmic rays are dealt with by the algorithm on board, but we do see cosmic rays, particularly if they're energetic. And if the jump persists over a couple of groups, they can cause artifacts, and then the algorithm will centroid on that cosmic ray artifact. Again, very difficult to mitigate and very difficult to predict. So with to protect against those particular occurrences, even though they are rare, we are moving to a 3-point dither strategy. So the near-infrared instruments already employ that strategy as well. This does protect much more effectively against, a hot pixel or a cosmic ray. This is not something that users really need to select anything. This is once we have sufficiently tested that, and that's still underway, it will just become the default way of doing target acquisition. Just there will be a small increase in time, because now for your TA exposure, we will do that 3 times, not just 1 time. But most TA exposures are very short, so we expect this to be a very, very tiny impact on people's time. And it will be applied for all TA, so chronography, LRS, and MRS. So we're kind of, just please do read on the requirements for target acquisition, and come to the help desk if you have any questions about how to get the most successful TA. And then we will also be moving to this dithered strategy that will protect against some of the really hard to predict issues that we see. All right, and that's it. Got 30 seconds to spare according to my clock. Wide field spectroscopy will be available in parallel from cycle 6. We have a whole set of new subarrays that will give better data quality, and for the LRS in particular, open up some new capabilities. We will have fast group average 8 readout pattern available for science, which will give much improved readout noise performance. and no longer get these problematic switching thermal artifacts, and then hopefully improving the success rate of target acquisition a little with the dithering. And as all the others have said, please come talk to us in the help desk. We are happy to help you prepare your MIRI observations.